Hi everyone. So in the previous video we introduced the Bellman equation and even used it to compute the value of a state. We also discussed the Markov Reward processes, which we define as a tuple of states, probabilities, gamma, and reward. The limitation of Markov Reward processes is they do not allow us to make decisions. Like there are no actions. The agent simply moves through the state and observe rewards without any control over the process. Today, we will introduce Markov Decision Processes, which give the agent control over its environment by allowing it to take actions. So, Markov Decision Processes, MDP. Okay, by the way, we have actually, hope you can see this, we have actually seen actions previously, like the agent going left or right, but in this video we will formally define them within the MDP framework. So the MDP is a tuple of states, probabilities, gamma. So this can be a probability matrix, a set of states, gamma, reward, and then a set of actions. So we're introducing actions here. Okay, so previously this is what we were looking at, this 4, but now we're introducing gamma. Okay, so this means that we have control over the rewards and the state transitions through our actions. Now we can also look at it this way. A next state could be is something like this: sk, a current state, and ak, and then a next reward that we receive is something like this: sk, ak, let's say k 0 1, and so on. So what it means here is, unlike Markov Reward processes where the next state sk plus 1 only depends on the current state sk, in Markov decision MDP the next state sk plus 1 depends on both the current state and the action that we take. Similarly, the next reward that we receive at each step is now a function of both the current state and the action chosen. Okay, this is really important. The next states, they depend on the actions that we take. It also means that we have a way to influence the Markov process and shape its trajectories. Okay, so maybe let me give you an example. But before then, let's quickly revise our Bellman equation. The value of a state is the reward, or like the immediate reward, expectation, S prime is the next state, then gamma, this is not y, value of a next state. Okay, by the way, this is not y, this is gamma, and we have already unrolled this in the previous video, so we know what what this is. So the system that we are going to be working with is something like this. All right, so this is like a 4x4 grid world. We have an agent that moves around. We have terminal states 0 and 15. Okay, now we can look at these parameters and fill them in. Starting from the state, well, we have 16 states. The probabilities, but before then, let's actually start with actions. Let's say actions A, right? Well, possible actions in any state could be left, right, up, and down. Okay, and then probability. Well, we're not going to define a probability matrix. What we are going to say is we are going to have a 0.25 for any action of, for example, left, right, up, and down. They are all going to have a probability of 0.25. When you sum them up, you'll end up with 1. And then reward, for any movement, we have a reward of, we are going to end up with a reward of -1. Okay, and finally gamma will be 0.9. All right, so now we have what we need. Even in programming, this is when you define this, then you can start maybe in a for loop, start computing maybe the values of a state. Let's actually compute the value of state 5 using the Bellman equation. Well, from state 5, what are the states that I can go to? I can go to state 1, 4, 6, and 9. Right? When I go from 5 and I go left, I'll end up with, when I go up, I'll end up in state 1, going left, state 4, going down, state 9, and going right, state 6. This is going to be something like this, where immediate reward, whatever I do, I have received a negative reward of -1 plus gamma 0.9 times, well, we iterate through all the possible states I can go to. Well, the probability of going to state 1 is 0.25 times the value of state 1, plus the probability of going to state 4 is 0.25 value of what? State 4. Probability of going to 6, 0.25 value of state 6, plus similarly value of state 9. Okay, and when you do this, you will end up with -1. So in programming, by the way, the initial values in programming of all the states, you can make them 0, for example. And if you repeat this process for all the states and iterate multiple times, the values are actually going to converge to the point that when you do this for all the states many times, you will end up with something like this. So like these are the final values of all the states. Okay. Now, now that we can evaluate the values of a state, the next question is how do we decide with which action to take? So imagine the agent is here, it finds itself here, and what is the best action to take to reach the terminal state? This is where policies come in. Okay, let's see, maybe I can define policies. Okay, let's see policy. Yeah, policy. This is where policy comes in. Think of policy as a function pi that takes in a state and tells us the action to take. Okay, there are two types of policies. A policy can be deterministic, like this one. For example, it could be like this. It can take in, let's say, state 3, and it can tell you to, for example, go left, something like that. A policy can also be stochastic. Now, this assign probabilities to actions. For example, you are in state 5. It can tell you to 50% go left, 50% go right. Stochastic policies will become more relevant when we start exploring reinforcement learning algorithms, where the agent learns to balance between exploration and exploitation, which are like two concepts that we'll be taking a look at later on. So at the beginning of the program, maybe you can define a random policy that tells the agent to go left. Whatever it is, just go left. But what we can actually do, we have gotten these values of all the states. we can do is for any state, pick the action that will lead to the state with the highest value. So for example here, from say 6, what is the action so that what is the action so that when I take it, I'll end up with a state with the highest value? Well, when I go left, I will end up with state 5, and which is actually the highest value, minus 0.66, compared to going to other states, minus 0.71, minus 0.71. This is actually the same. You can go left or you can go down. We can see that the best policy is going left or right, going left or down. You can do this for all the states, and you will end up with something like this. Okay, so for all the states, pick the action that will lead to the state with the highest value. Similarly, let's say here, well, when I go up or when I go right, I will end up with state 5 or 10. They have the highest values, and that is why, for example, in state 9, the policy, a better policy that we have driven from the values is going right. Okay, so what we did is we have gotten the values and we derived a policy from the values. Yes, so this is all. Thanks for watching. In the next video, we will look at optimal policies, optimal value functions, and the state action value function, also known as the Q function. And by the way, there's going to be a Jupyter notebook as usual that you can take a look at. Thank you very much.